Hey, Algebra 2 friends, welcome. It's your first one of these in a while. Got my colors ready, and make sure that you're powering your, oh, where do they go? There you go. It's power your problems with pretzels. Never do math without carbs. Okay? All right, I'm going to quickly review a few things from the Arthur Benjamin video and from the lesson a few days ago about complex numbers, and then I'm going to go above and beyond for you today. Hopefully we'll not overdo it on the length of the video today. I want you to learn how to do your stuff on your lesson. No, I need water. Okay, well, whatever. We're learning about Tartaglia and Cardano and those guys. They're doing math. Cardano is actually famous for a first time in his writing speaking about an example he was doing where he had the square root of negative 15 in his work, and he's like, I don't get it, but I'm going to start using it, and I need it. You can watch YouTube video, number 5 video on square root of negative 15. Type that in. You should watch it. Barry Mazer, I believe, is the guy that they're interviewing. He's really good. Give you the history on that. Okay, so in review, a complex number is a two-dimensional number. It's got a real part and an imaginary part. And when we write these numbers, we write them like this: a plus bi, where a is the real part and b is the imaginary part. The imaginary part has an I in there. We start off by doing this. We said, let's define I squared as negative 1 so that we can square something and get a negative. Okay, if we want to do it, let's just do it. And that lends to the definition that I equals the square root of negative 1. So if we're ever working on a quadratic equation and we've got underneath the radical sign the b squared minus 4ac part, and it ends up being negative, that's okay. We can still find solutions to our parabola, our quadratic equation. It just won't be real number solutions. You won't see them cross the x-axis. We're still going to have two answers, and they will be complex conjugates of each other. So this is what we thought was all the numbers that we could ever work with, were all the real numbers, like negatives and positive integers and the number 0 and fractions and decimals and whatnot. And then they added, irrational numbers and all that kind of stuff too. But then we found out that we could actually use these imaginary number things, square roots of negative numbers like square root of negative 15, or as we started writing these things like 3i or even negative 2/3 I. And if you take both of those together, first dimension and the second dimension, you get a two-dimensional number that's the whole set of complex numbers. In saying that way, you can actually have a number like 2i that seems to be only imaginary, but really it's got a real part of 0. Or just have a real number and it actually has an imaginary part of 0i. So they are still complex numbers. Real numbers are complex numbers. It's just their imaginary parts is 0. And 3i is a complex number. It's just its real part is 0. So I've got here 4 complex numbers to graph. So we learned about that. We'll have, instead of the x-axis and the y-axis, we'll have the real number axis and the imaginary number axis. And the a number goes along this way like x would, and our b number in our complex number goes in the vertical direction. So I've already graphed the complex number 3 plus 2i. I go out 3 on the real axis and up 2 in the I direction. So we get this one number with 2 dimensions to it. It's very similar to x and y addresses, except it's on the complex plane rather than on the coordinate plane. Let me graph this one. 2i, where's that going to be? Or if I think of it as 0 plus 2i, it's going to be right there. And how about 3 plus 0i? It's going to be right there. Negative 1 plus 2i, we'll go negative, this was negative 1 right here. Negative 1 and then up to 2i. You hear that? You hear that? You know what that means? And this last one, negative 2 minus 4i, we go out to negative 2, and then we drop down here. There's negative 2 minus 4i. So graphing complex numbers is really easy. You can use your regular grid paper, just label it real and imaginary, and off you go with plotting those points. Just the same as you would x, y points, except it's like A and B. Okay? Gotta talk to you about another thing, and that'll be over here. Let me erase this, get this off the board. We don't need that. Graphing, we did that. Okay, we have something that we want to know about this complex number. We can write it in more than one way. There's this way where we have the real and the imaginary parts, but we could also, oftentimes we're often concerned about how far that point is from the origin in the complex plane. Sorry, that's like a curvy line. It should be straight. I would like to know this distance. And so this is the exact same kind of math as Pythagorean stuff, because we have here A and B, right? We have a distance A on the real number line. We have distance B in the imaginary direction. And we're saying that's where we ended up, was at 4 plus 3i. Okay, I think maybe you're sniffing out where this is going to go. We would like to know this distance here, which is given the symbol z for a complex number, and then it's got these absolute value signs on it. I'll tell you why the absolute value sign thing comes up here in a bit. But that is in math world, that's called the modulus. The modulus, the distance from the origin to that complex number. All complex numbers are given the set z or z, depending on where you're from. And we want to find the distance from the origin out to that point. The distance is really simple to calculate. As you can see here, we got A and B, and we've got a Pythagorean setup here. So we're going to say that distance is equal to square root of A squared and B squared. Okay, that is absolute value of A plus BI, the complex number. It's going to be take the A number and square it, take the B number, square it, sum them, take the square root. So what do we got over here? The A side here is 4. The B side here is 3. You want to take the absolute value of 4 plus 3i. You'll go 4 squared plus 3 squared. That's 16 plus 9 is 25. And so our answer is 5. That is a distance of 5 units from the origin out to our number. And I picked those ones because I knew they'd be easy, but it doesn't matter. You might be left with a square root. One thing to note about this, and you're taking notes, so write this down, is that the modulus, or the absolute value of a complex number, is always going to be a positive value. And there's good reason for that. We were saying this is the absolute value. Okay, absolute values are always positive values, or 0. They're never negative. Even if we got a complex number down here in quadrant 3, and let's imagine it's like 2 this way and 1.5 this way. So we have like negative 2. We'd have negative 2 minus 1.5i. Gotta answer this. My wife loves me. I love her. Oh yeah, this negative deal. All right, well, if the complex number's down here, it's still just a positive distance away from the origin. And in this case, we'd be looking at negative 2 squared plus negative 1.5 squared. That's it. No big deal. Calculator can do that for you. Whether you need an estimate or you need an exact answer, like a square root of something, it's okay. Negatives get squared, negatives get squared, it gets added to a positive number. No problem. Your calculator can do that. Also, if you're interested, you can go on your calculator to your Science Tools setting. And if you go over to, let's see, go to my apps, science tools. I'm going to pick number 4 on the list, vector calculator. You note that it has both an XY version and an R theta version. That's basically what we're doing here. So for instance, if I typed in like AB instead of XY, 4 and 3 for X and Y, I can just push this other button down here, R and theta, and it'll tell me the radius is 5, and then it tells me the angle. So switch back and forth between regular coordinate system and the polar system is very much the same as going from regular complex number answer to the modulus and the angle. Might be something you want to look at. It's not hard math though, so it's just Pythagoras. We've done this kind of stuff before. You have it in another lesson. Okay, that's pretty straightforward, I think. And you definitely want to have that formula down in your notes. You can hit pause if you want to. What's next? Multiplication of complex numbers. Whoa, we got blurry right there for a minute. As long as your calculator is set to A plus BI mode, see that? Next to real, set it to A plus BI mode, you can do math with complex numbers on your calculator. Now, you should know how to do it regular because it's super easy. Ben Arthur told you how to do this. We can take something like, ooh, what do we got in the book? Negative 4i times the complex number. Obviously, they're both complex numbers. I just said that. This is just distribution. We can treat that I like it's x. You get negative 28i plus negative 4i times 3i. Now this part ends up being negative 12i squared, but I squared is equal to negative 1. We said that before, so we get negative 28i plus 12, or better yet, we need to put the 12 in front and the 28 behind. We get a complex number when we do our distribution. An interesting thing to do would be to graph these as arrows and then figure out where we end up and try to guess what happened. Arthur talked about that too. So that's just distribution, and then we need to make sure that we write it in standard form of the real part and then the imaginary part for our complex number. Piece of cake. How about a 2D complex by another 2D complex like 5 plus 4i times 6 minus 2i. That's what we do. And then we bear with the consequences of what happens. So let's look at this. We get 5 times 6 is 30. And then we go outside, we go minus 10i. Then we go inside, and we got 24i. And then we got minus 8. I times I is I squared. I'm going to combine these middle parts here to get a positive 14i. And then we got that to deal with. I squared in there is equal to, say it, negative 1. That's right. Here we go. Negative 1. So this part that had the I squared actually becomes a real number. And I'm going to add it, combine it with this 30 here. You have 30, and then what happens? Plus 8. And then those two pieces there made a 14i, kind of like turns around, and we get 38 plus 14i. There's our complex number. Okay, take a complex number, multiply by another complex number, and you get a complex number. Now I'm just going to double check on this on my calculator. 6 minus 2i in parentheses, and I get my answer 38 plus 14i. Where's the I on here? Down here. You got to use your blue button. Second button, it's above the decimal point. So watch. Second dot makes I. I can square it. And then what happens? It already knows. It knows. Sorry. It's negative 1. It's negative 1. Ain't that cool? Pretty cool. How neat is that? Pretty neat. Pretty neat. So treat it like a regular thing until you get to one of these and you get an I squared. And then I think you know what to do. I also need to talk about powers of I and a kind of math called modular math. Doesn't that sound fun? Let's imagine that we've got a really weird clock, okay? And this clock only has 4 numbers on it. 0, 1, 2, and 3. And so we start our clock here, and our clock is going to go anti-clockwise. So that's another reason why it's a weird clock, okay? It's a weird clock. This is the way the modular math works. Basically, with powers of I to the 1, I squared, I cubed, I to the 4th, etc., we're going to see a pattern with these things. So draw a weird clock here, and then I'll explain what's going on in a minute. So let's start with I. I to the 1 equals I. I squared equals negative 1. I cubed equals, well, I squared times I. And remember, I squared equals negative 1. So we get negative I out of that. Okay? I to the 4th equals an I squared and another I squared, which means that's negative 1 times another negative 1, which is just 1. So let's imagine that we started with 1 and then we multiplied that by I once. We would get 1 I. And now if we multiply I by I again, we get I squared, which is negative 1. If we multiply I squared by I again, we'll get negative I. And if we multiply I cubed by I again, we get I to the 4th, which is 1. I want you to notice we got back to where we started. 1 times I times I times I again times I, and we get these answers. And we're only ever going to get these answers because what happens if I go I to the 5th? Well, I to the 5th is I to the 4th times I to the 1. I to the 4th is 1, and I to the 1 is I. So we're back there. I to the 6th would be I to the 4th times I squared. I to the 4th was 1, and I squared is negative 1. Negative 1. I'm just back to this spot right here. And so maybe you can see what I'm doing here with this thing here. The basic rule for this repeating pattern, if I wanted to keep going, and you can go backwards and repeat this stuff, but basically there we go. There's our pattern of stuff. Is that we're going to take that power of I, and we're going to divide it by 4, and then we're going to take the remainder. And that is I to the power of. It's equal to that, I to the power of the remainder. So if I add I to the 4th, I'm going to divide that power of I by 4, and I get 1. So that means I to the 4th is equal to I to the 1. Is that correct? No, it's just equal to 1. Oh, I get a remainder of 0. Yeah, there's it does it perfectly. Remainder 0. So there we go. It would be I to the 0, which is equal to 1. There we go. Or maybe I'll pick something else that's better than that. Let's say we had I to the 7th. Okay, well, 7 divided by 4 is 1, remainder 3. So this is the same thing as I cubed. Let me just demonstrate this to you, okay? Let's say we have 0, And then we go I to the 1, I squared, I cubed. I to the 4th is the same thing as 1. And then we have I to the 5th is the same thing as I to the 1. I to the 6th is the same thing as that. I to the 7th was the same thing as I cubed. And I to the 8th will be the same thing as I to the 4th, which is the same thing as 1. So we could keep going around the circle forever. We could take something like I to the 101 power. We can figure out what that's equivalent to. Take 101 divided by 4, which is 25 remainder 1. I take that remainder and I say that's the same thing as I to the 1. It's a brilliant math pattern. So it's like saying, hey, what time is it going to be in 27 hours? We can just divide that 27 by 12, and we go around the clock, and we've got a remainder of 3. It's going to be 3 hours from now. That's how that works. That's called modular math or clock math. About I to the 23rd, 23 divided by 4, that's 5 remainder 3. I cubed is the same thing as I to the 20th power. I cubed is I squared times I, so we get negative I. And that's your answer. And that's your answer. Basically, every time you multiply by pi, you get a 90-degree rotation. We'll explain that some other time. Righty then. Your calculator knows. Try it. Put in your calculator I to the power of 17. Okay? I to the 17th power, and it's going to kind of sort that out, and that's just I, or I to the 1. If I put in I to the 18th power, it's just negative 1 because it's the same thing as I squared. So glad that you bought that calculator, didn't you? Aren't you? Whatever. Oh my word. Okay. Division. In general, use your calculator. But not in general. We want to take one complex number and divide it by another complex number. The way that we're going to fix that is basically what we've got here is a square root in the denominator. And the way that we fixed that before was we used a conjugate. So that would be the key to doing that. It's a little clunky on the top, but we already did multiplication. It's this business down here in the denominator that I'm really interested in. If you take a complex number and its conjugate, look what you get. A squared minus ABI plus ABI minus B squared I squared. These two cancel each other out. We're left with A squared minus B squared I squared. But I squared is negative 1. And so negative B squared times negative 1 equals A squared plus B squared, the sum of two squares. The sum of two squares can factor down into two complex conjugates of each other. So we saw that in the video. And if we were trying to do 2 plus 3i divided by 4 minus 3i, we would fix this. We would take the top part and multiply by 4 plus 3i, and I don't really care what that is right now. And we take the bottom part, 4 plus 3i, and we make it really super easy. It's going to be a squared plus b squared. 4 squared plus 3 squared. That kind of looks familiar, right? We saw it in the modulus problem. 4 squared is 16. 3 squared is 9. We get a number down here of 25 without any i's on it. And then we just do the top, and we got a fraction with a real number in the bottom rather than a complex number in the bottom. That's one of my favorites, is the complex conjugate thing. A plus bi times a minus bi equals a squared plus b squared. It's brilliant. Again, your calculator knows how to do this. Give it that fraction bar. Use the little I button, and out will pop the right answers. One of those examples is 4 plus I over 6I. Complex conjugate of 6I is negative 6I. And if you want to think of it this way, it's 0 plus 6I times 0 minus 6I. Up here, we just need to do by minus 6I, and that's distribution. And down here, this is the sum of two squares, 0 squared and 6 squared. It'll be over 36. On the top, we'll have negative 24I minus 6I squared. I squared is negative 1. That makes this one equal a plus 6. And I just need to rearrange the parts. That one turns into this 6 minus 24I over 36. And then typically we split that up into real imaginary parts. 6/36 minus 24/36 I, or 1/6 minus 2/3 I. You want to double check? Doing a calculator. Look at the original problem. The original problem was 4 plus I over 6I. Okay? 4 plus I over 6I. Now I'm going to hit enter. I get 1/6 minus 2/3 I. My suggestion is you try it by hand a few times, and then you're going to trust your calculator to do that work for you. You understand how complex numbers work. Later on, we can visualize this, and you can see it, what's going on, and that's really interesting. Again, why in the world are we talking about complex numbers? Because we use it in quadratics. It happens in answers to quadratics. So let's say you're going along and you're able to complete the square, and you get to the point where you're like this. I know you're going to have a problem, because if you take the square root of both sides to solve for x, then you've got the square root of a negative number. But now there's no problem. Something squared is x plus 12. That's equal to the square root of 144, which is 144 and the square root of negative 1 if we break it up. That part's I and this part's 12. Finish it off like this, negative 12 plus or minus. We get two answers. Oops, don't forget that negative out there. We get two answers that are complex conjugates. Negative 12 plus 2I, negative 12 minus 2I. Multiply those two back together and see what you get. It's an interesting little problem. So when we're doing x equals negative b plus minus the square root of b squared minus 4ac over 2a, sometimes underneath that radical sign, we're going to be subtracting more than we've squared here, and that's the case where we're going to have two complex conjugates as answers. We're going to have a graph that's something like this, that has no places where it crosses the x-axis, but we still have two solutions. They're complex numbers. You're welcome. Check your email for the problems that you're supposed to do. God bless America.